But you see, you saw the feedback. Did you? I'll talk about it.
So this I got a problem last time.
Okay, let's get started. Okay. Welcome back to our software testing and the quality assurance class. Okay. Right before today's class, I was trying to finish up with all the grading for the midterm exam, but then I noticed that I'm still missing a couple, and I need to find out why, and things it could be because one of the students maybe dropped the class, or and I'm still missing another one, and so I need to get that resolved before I can talk about the midterm exam and do a review. But for the rest of you, I have posted your midterm grade in the Blackboard. Okay, so at least you can look at your grade and get an idea how well you did there. But if you do have some specific questions, don't ask me now. Wait until probably next week. I will go over the midterm exam questions and review the questions and the answers, and so we can kind of learn from our mistakes. Yeah, of course. Even if you did a good job, you can still probably benefit a little bit from looking at other people's different opinions and answers, and so that will be beneficial as well. Okay. In general, I think I'm pleased with the exam results. Okay, and so far among the ones I graded, the lowest is not that terrible, and the highest is 98. Okay, so that's really good. Okay, and so I will be most people. I think the average is in the 80s. Okay, so that's kind of give you a little bit perspective when you look at the score you have and what that means. Okay, and so that's about midterm exam. I still need to find out about the two exams I'm missing now, and then we can discuss their exam questions in class. Okay, so that's about midterm exam. And for the project proposal, okay, I haven't quite finished grading them all, but I did go through a substantial part of it. But seems to be that I had some problem with this time with posting a grade because when I look at the attempt and try to grade things and try to give feedback, there's some problem with the with posting the numerical score. So I need to figure that out. But for now, if you check, if you see some feedback, then you are okay. Okay. If you haven't seen, if you don't see the feedback, probably I haven't got that far yet. Okay. And so I'll try to finish providing some feedback to every one of you in the next couple of days. Okay. So it's just been a hectic last few weeks because of several meetings and things. Conferences that I need to organize and I need to attend. So I apologize for the delay, but I'll try to catch up and try to provide everyone with some feedback in the next couple of days. So some of you have seen some feedback, right? No? Anyone have seen some feedback? Even without score.
Yeah.
No one saw the feedback?
You're talking about the
Proposal, project proposal. Didn't see anything on the blackboard? I finished about maybe about half or maybe a little bit more than half of the ones. That's
the grade. Just the grade.
No, the project proposal.
Yeah.
Yeah, we have the one.
Yeah, we have the grade, but without the feedback.
For each one of them, I did enter some particular comments. Okay. No? So,
No comment, no.
yeah, from my side, it seems to be that I can see the feedback, but I can't see the grade. And, okay, I need to figure that out. Okay, but from my side, I can see the things that there must be some problem with my Blackboard interface or something. So I need to figure that out, okay, in the next couple of days, okay. And all the ones I have seen seems to be okay. I had some specific feedback about what area you should pay attention to, but generally the ideas are generally in the right direction, okay. So the ones I have seen, okay. So I'll try to catch up with that and figure out what's wrong with my end of the Blackboard and make sure it's going to you will be able to see its feedback. Okay. Okay. So those are about the midterm and the project proposal. Okay. And now we have finished. Let me turn to this desk camera. Okay. So we have finished with the material before the midterm exam, and so with the testing part, okay, we looked at their checklist, okay, and then we really looking at the formalize the checklist and have some nice properties with their partitions. Partition testing, okay, and then from partition testing we kind of branched off to two of the things that's kind of with the uniform partition test. So basically sample one thing from each of the partitions, okay, and then we look at the non-uniform partition testing. So one is the UBST. With Musa OP, okay, and then the other one we looked at is boundary testing. Okay, so we kind of stopped there, looking at their different testing techniques. Okay, but when we look at this from the checklist to partition, we were looking at why we were trying to do the checklist to partition, because we look at some of the problems. Okay, problems with checklist. Problems with checklist. Okay, we looked at the problems with checklist. Basically, when you just look at the checklist, using checklist for testing, we saw there are some problems with it. For one thing, you may leave some of the things uncovered. Okay, so we have some kind of holes in the checklist. Okay, so something that kind of a lack of coverage. So some kind of a lack of coverage. Some of the things are not, left out. Okay, and then we say, okay, that's not good. Okay, then we have some overlaps. Okay, some of those things we try to solve those problems by looking at the partitions, okay? Solve those problems by looking at the partitions, because when we look at the partitions, essentially, we try to make things mutually exclusive, so there's no overlaps, okay? And make them collectively exhaustive, so that they will not leave any holes, obvious holes out, okay, because we will have some of the things for each of the partition subset, some of the things that represent the whole subset, okay. But then we have also some problem with the complex operations or sequences and steps, okay, repetition, repeat, and so on. So some kind of complex operations with sequences, steps, repeats, and cycles and that kind of things. We cannot really do a very good job with using checklist-based testing, and which cannot be really comfortably and adequately addressed with our MUSES operational profiles, the UBST, or with the boundary testing either. Okay, question there?
Oh, no, just.
Yeah, okay. So, yeah, so we do have some of those problems, and they say, okay, we cannot really solve that kind of problem with just a partition testing, so we need to do something more, and doing something in addition to what we did before, okay? So this is where this is the primary reason, and those two things are also kind of a secondary reason for us to look at the finite state machines, okay? We will be looking at the finite state machines and then also finite state machine extensions to do some of the testing. So that's kind of the introduction by way of what we have seen so far with the testing techniques, okay? Looking at the use of finite state machines for our testing purposes, okay? So that's what we are going to focus on in today's class, and then we will be with the follow-up classes for the next 4 weeks, okay? So we will be looking at basically for basic finite state machine testing, and then looking at extending finite state machines to support usage-based statistical testing. Okay, so that will be something kind of something along the line of UBST with MUSE operational profiles, where we are using the flat underlying model. Now with the finite state machine as that underlying model, we can have some kind of thing along that line of MUSE's operational profile, but with the finite state machine as the underlying model, but with some of the probability information about the usage. Okay, so how often different things are used. Okay, so we'll be looking at that, and then also we'll be looking at some of the extensions of finite state machines to cover certain things. With the partitions, we look at the extension for that to cover the boundaries. So with the finite state machines, because we are looking at state and state transitions, we want to look at the whole sequences of state transitions. And so we'll be looking at the so-called control flow and the data flow, okay? So we'll be looking at so-called Markov operational profile, okay? And then we'll be looking at the CFT and DFT, control flow and data flow testing, okay? So those are the things, so the basic finite state machine, Markov operational profile, control flow testing, and data flow testing will be the focus of our next 4 weeks of class, okay? And after that, we will try to wrap up the testing part by looking at some of the other related and important testing techniques, and also some of the common issues with testing, looking at testing different techniques applied to different subphases, and looking at testing from different perspectives, and some comparison, some kind of integration of different testing techniques in our overall strategy for testing. Okay, so we'll be looking at those, and then after that we'll be looking at a little bit more of the other QA techniques, as well as the analysis and feedback issues related to testing. Okay, so those are the things that we will be looking at starting with today's class. Okay, and that is a kind of an introduction from what kind of linking what we have seen so far to what we we will be seeing in the next few weeks in the remainder of the semester. Okay. So let me return back to our class slides. Okay. Yeah, this implementation PC here. Okay. So our next big topic is the one from chapter 10. Essentially, it's what we call the coverage and the usage testing based on finite state machines and Markov chains. Okay, and so that's kind of like two distinct subjects, but kind of closely related. It's kind of similar to the basic partition testing and the Musa's operational profile testing, that the relationships there. Okay, so what we will be doing is to first introduce the finite state machines. What are the finite state machines? What kind of information is captured in the captured and represented in the finite state machines? Okay, and then we'll be looking at the finite state machine based testing, and if you do the finite state machine based testing, what are the things that you will be doing? Okay, and before the end of today's class, I think we will be having some time to introduce some concept about the Markov chains as an extension of finite state machines. Okay, and then we will be looking at the Markov chains and the extension of Markov chains that we call the uniform Markov models. So they are basically a collection of Markov operational profiles that are used for testing, and we will be looking at some of the case studies using this kind of things for testing as well. Okay, so that's basically what we will be covering in the today's class and the next week's class. Okay, and then after that, as I mentioned, we will be extending the finite state machines to look at some of the specific problems that we can address related to the execution paths, relate to the data relations in their among the execution components. Okay, so let's look at the things. Okay, so we kind of talked about their motivations for finite state machines. Okay, essentially we mentioned about that there may be complex or complicated operations or operational sequences that is hard to represent in their checklists of partitions or Musa's operational profiles or boundaries, those kind of things. Okay, so we want to model those kind of things. Okay, so whenever when you look at the system behavior or look at the system implementation, if you have some of the things, some of the kind of cycles, some kind of a repetition involved, typically with checklist and partitions, we do have some difficulties with them. Okay, so well, that's one of the basic reasons for us to look at the finite state machines. Okay, but from that's kind of from the need side that we need finite state machines. But also we also looking at from the opportunity side, looking at oftentimes we do have some of the models for the system that we may be able to use for testing as well. Okay, so some of the models exist for the system, for specification, for clarification, for some various other purposes, for design, and the various implementation of various other purposes. We may be able to use those kind of things for testing as well. Okay, and as we go through the design and go through some of those requirements, specification, design, implementation, one of the powerful tool that people have often used is the finite state machine. Okay, and flow graphs, finite state machines, all kinds of things. Those diagrams that link things together and back and forth and going back and forth and then with some repetition and things. Those are the bases that we may be able to use for our testing purposes. Okay, so for example, we mentioned about a little bit about the with respect to formal verification and the formal specification, okay, the formal method. We said the formal method consists of formal specification and the formal verification. Formal specification can take two kinds of forms. One form is the so-called descriptive formal specification. Okay, so essentially that gives you some kind of logical conditions about the program execution before some program execution and after some program execution. Okay, and another type of formal specification is really a finite state machine. Okay, that's oftentimes in the specification requirement analysis and product specification area, people call that a behavioral specification. Looking at the behavior, a behavior can often be stated and well described with a state machine. Okay, under this kind of situation, with this kind of input, this is what you should do. Okay, and then you link those things together to form your behavior specification. Okay, when we design the system, when we implement the system, we probably had a lot of block diagrams and sketches. Okay, looking at this thing goes here, this thing goes there, and so on and so forth. Okay, and occasionally, and actually more often than not, we will have some kind of loops or some kind of cycles. Okay, so you go through this thing and then can go back to some other thing again. Okay, so it's very often we have those kind of things. So if we can make use of those things for testing purpose as well, it will save us some time and as well as give us some more directions about what specific things we need to target, we need to test. Okay, so that's kind of from the opportunity side. Okay, we can do that. And also another thing from the opportunity side is that we can look at with their partitions and with the mutual operational profiles, boundaries, we're kind of looking at the global picture. Okay, looking at the global picture, what's the overall input and what's the overall output. Okay, and we are not really looking at the local picture. Okay, and sometimes that those global picture may be hard to grasp and hard to get the precise information about, and to analyze, to model, and to test. Okay, so sometimes those information relate to some of the local areas may be easier to obtain and to get. Okay, so that's the case. Then we can use those kind of things in local areas, and instead of looking at the overall situation, we look at under this specific situation. This is the information I can get, and this is the things I can do, and that will help us with testing. Okay, so with that we can model a lot of those things and capture a lot of those things and represent a lot of those things in our finite state machines. Okay, so that's kind of looking at the need and opportunities for finite state machines. Okay, but then we need to kind of have a good understanding of what is a finite state machine, and then we can then look at how do we represent the information in the finite state machine, how do we use the information in the finite state machine for testing purposes. Okay, so finite state machine, as it implies, that we have states. Okay, and the states, the number of states is finite. Okay, so that's why we call the finite state machine. Okay, so we have a number of states. Okay, and then the thing with the states, if you say, oh, they are just unrelated states, and I have a collection of the states. Well, if you have this something unrelated, or you have a collection of states, and you can group them, then you can use the sets and use the partitions and the things. Okay, but then once you connect them in a certain way, just by grouping them, just by partition them, may not make as much sense. Okay, so we have a lot of so-called transitions or linkages or links between pairs of states, typically. Okay, in this case, we kind of typically deal with the pairs of states. Okay, from one state to another state to another state to another state to another state. Okay, and so on and so forth. So we look at the pairwise relationships among the different states. Okay, so sometimes those things can be looking at you go from one state to another as a kind of required precedence relationship. You must do this before you do that. Okay, and sometimes you can think of with the next state is a follow-up to the current state when I encounter some kind of input. Okay, so I'm in this state. Well, when I receive this input, I'll go transition to your state. If I receive something different, I translate it to a different state. Okay, and so I need to look at this so-called transitions. Okay, so those states are not isolated states; they are interconnected. Okay, so typically we are looking at this binary kind of unidirectional connections. Okay, so from A to B is different from B to A. Okay, so we have to make that kind of distinction. So we have links and we have directions. Okay, and so what we have there is that we do have a directed graph of the states. Okay, so the states are connected. Okay, and then as with our previous testing models, with our kind of partition models, we typically have some kind of input-output relationships there. Okay, so in the finite state machines, we will also have some input and output associated with the different states. Okay, so we'll be looking at the input and output associated with the different states, or maybe with the state transitions. While you encounter with this input, you will go to another state accompanied by some output. Okay, so in the finite state machine, in the traditional finite state machine, input and output are typically in the traditional finite state machine, input and output are represented on as some property associated with the transitions. Okay. Now later on we'll see some variations that you may also associate the input-output with some of the states as well. And so essentially what we have there is the four important elements, okay, with the finite state machines: states, transitions, input, and output. Okay. So those are the four things that we will be using to specify finite state machines. Okay. And then sometimes we have some of the complete operations. Okay. And when you look at the complete operations, is basically you go from some initial state, go through a number of intermediate states, accompanied by the input and output during those transitions, and then arriving at the final state. Okay. So when you chain all those things together, state, transitions, input and output, okay, in a overall chain, that we'll be looking at some of the complete operations. And actually, one of the important testing techniques that we will be spending our time on will be the control flow testing. Basically, it will be looking at the entry-exit complete execution paths, and then looking at how do you test those different execution paths, and how do you model those things, how do you come up with test cases, and how do you perform the test, check the result, and follow up on the results as well. Okay. So that's a basic idea of a finite state machine. We do have a couple of examples, so let's look at one example first before we go further with those finite state machines. Okay. So this is an example from a textbook. Okay. It's an example about their state transition diagram for a cellular communication system. Okay. So essentially, for a cellular, this is based on at the time when I was working on this, I was working with a colleague of mine, Eric Lin, and we were working on some of the telecommunication problems, and so we followed this IS-95 standards and looking at their specification for this cellular communication. Okay, come up with this kind of a financed machine, and actually we were extending those things to do the usage-based statistical testing for those telecommunication systems. Okay, so in this system this is actually based on the standards or the specification documents for this cellular communication system. Okay, so you look at this here with the system. First, you power up the system. Okay, so while you are doing the power up, that's a kind of a state you are powering up. Okay, and then after power is up, you go into a state of try to initialize something. Okay, so you try to initialize the mobile station initialization. Okay, and when your mobile station after it's initialized, it's basically it's ready to use. Okay, and so it's enter into a state to say, I'm ready to use. I'm waiting for a command. Okay, I'm idle and I'm ready. Okay, I'm ready to serve you. Okay, so looking at some of the looking to process received messages. Okay, so then you receive some messages. Okay, so you receive some paging channel message. Okay, when you receive a paging channel message, then you go into the so-called system access state. Try to do the system access. Okay, and then when you do the system access, you some of the message maybe someone want to make a call. Okay, and so then if that's the case, then you making a call and go into this state that you have mobile station control on the traffic channel. Okay, so try to establish traffic channel, maintain that traffic channel, allow people to communicate. Okay, when you do the system access, then when you receive the message is not making a call, message is doing some other things. You do it and go back and wait for the system to receive some additional requests and process those kind of things. Okay, and so if you are making a call, then you'll have a mobile station control on the traffic channel. Okay, monitor establishing the channel, monitoring the channel, make sure that you are communicating correctly, and then after you finish that, you need to do some kind of maintenance job. Make sure that this whatever capacity and the resources allocated to this customer user and to make complete this call will be deallocated. Okay, and will be ready to use it for someone else. So you go back to some kind of cleanup stage, which is essentially the same as some kind of initialization. Make sure that your whole system is ready to use. Okay, so you go back to some kind of a system initialization, a cleanup here in this case, and then after that you'll go back to the idle state. Okay, so in a sense, is that in your system you are either waiting for command or processing some command. Okay, but there are some other transitions from power up, you do this, do this, do this, and then when you look at this, well, we can see a number of characteristics of finance state machines. Okay, the first one we said, what are the finance state machines? They have 4 elements: states, transitions, input, and output. Okay, so those are the 4 basic elements of finance state machines. So for this one, let's say what are the states? So the collection of the states are A, B, C, D, E. Okay, you say, okay, I don't care about their relationships. I just care about states. Well, if you just care about states, then you can say, this, I do have a checklist. And then I will say, are those checklists, those items, are they mutually exclusive? Are they collectively exhaustive? You can say, okay, those things covers all the high-level states. Okay, and none of them are the overlap with another one. So then you can say, okay, they are form A, B, C, D, E form a partition. You can do partition-based testing. Okay, you say, okay, I want to make sure that A works, B works, C works, D works, and E works. You can do that. Okay, so you see here, it's good for us to understand the basic partitions. Okay, and then that will be used for as a part of the basis for our finite state machine testing as well. When we come identify the states will be different from each other. Okay, and they are mutually exclusive, and they are collectively exhaustive. Okay, and so they are different from one another, and then they collectively represent all the possible states for our system. Okay, so that is a partition. Okay, so the sum of the elements in our finite state machine really forms a partition, and so it's good for us to have that background, that kind of basis of knowledge before we move on to the next step. Okay, and then that's a state, but we say, okay, they are not just states, they are mutually exclusive and collectively exhaustive, that's it. They have relationships beyond that the being mutually exclusive and collectively exhaustive. They have additional connections. So for example, here, from power up, you always, once power is up, you always go to mobile station initialization. Okay, so in this case, it's an unconditional transition. So from this one, you always go to this one. Okay, but for other transitions, sometimes you have unconditional, sometimes you have conditional. So for this one, after you finish with the initialization, you always get ready and waiting for something. Okay, so this is an unconditional transition here. But over here, well, there is a conditional transition. You can either go down this way, or you can go up that way. Okay, go down this way or go up that way depends on some of the conditions. And in this case, the conditions are represented by the messages, or by the some of the system kind of characteristics. Okay, so if you receive a paging channel message, then you go this way. If you are unable to receive any message, after a while you say there must be something wrong. Okay, there may be some general expectations about the paging channel message. There must be some message coming into the system because your system is in use and some traffic will be arriving. If you cannot see any of the traffic, then that means something's wrong. And then you can say, okay, I'm able to receive paging channel. Then you need to go back to do the reinitialization. If you receive some paging channel message, then you go on to process that paging channel message. Okay. Of course, in here, the process is kind of divided into processing this kind of thing or processing something else. Okay. So essentially, over here, we have conditional transitions. Either go this way or go this way. Depends on some condition, and in this case, depends on some input. Okay. So if your transition is dependent on input, then what you need to do is here in your model, you need to kind of examine your input. Look at your input. Is your input overlapping, or they cover everything, or not? Okay. This is actually one of the important parts that what we learned about the partitions also come into play. Because if you look at all the possible input I need to handle from a state, then all the possible input need to be partitioned. They need to be mutually exclusive, and they need to be collectively exhaustive. So essentially, when I define my system, I want to make sure for every input, I will have one and only one correct response. Okay. So if I receive an input, I don't know how to handle it. What's that mean? That means that I need to make a transition, but I don't know where to go. That's the situation. So in the finite state machines, that will be represented by some of the problems with the missing states, probably. Because I have some input, I don't know what to do with it. So I'm going to do a transition, but I don't know where to go. Okay, so that maybe some of the things with you didn't identify all the states. Okay, so you say, okay, under this input, what do you do? I don't know. Well, you better know, because if you don't know in the actual situation, if this happens, you don't know what to do, and then your system is not going expected to be functioning correctly. Okay, so that is some problem. Okay, and then what about if you have some input? I can follow multiple transitions. Well, in that case, which transition should you follow? I don't know. If you don't know, then there's this contradiction here. Okay, so that's the kind of like in our partition testing, we look at the underdefined and overdefined situation, ambiguity and the contradiction. Ambiguity is some of the things I don't know what to do. Okay, it's not specified, so it's ambiguous. Okay, and there are also situations say that you belong to both of them, that you belong to all three of them or four of them, and then you don't know which one to select. So you have a contradiction, because one set said, okay, well, if you have this input, you should do this, and then another one said you should do something. So you create a contradiction. Okay, so that is another part of the testing when we try to perform testing with finite state machines. We can always looking at the conditions on the input, that looking at the input associated with the outgoing transitions. Are those all the outgoing transitions and the associated input, do they form a partition or not? Okay, if they form a partition, good. If not, then there is a problem. Either you don't know where to go, or you have conflicting or contradictory directions about going to A and B and C and all the different things. Okay, so we see that also plays a very important role. Okay, and then so we talked about the states. Okay, A, B, C, D, E. We talked about transitions, A to B, B to C, C to D, and C to B, and so on and so forth. So transitions. We talked about the input. Okay, so input associated with those, particularly associated with those conditional transitions. Okay, and we haven't talked about output. Okay, so in a sense, in a lot of the systems, the output is a part of the things where you go. So you are making a call and you are producing some of the thing, and then lots of things, the mobile station control on traffic channel may be related to the things you do. Okay, so output in the traditional finite state machine is supposed to be always represented in the finite state machine. Okay, but oftentimes that may be implicitly represented. That we say, okay, there are some output associated there, but we may not explicitly list the output associated with certain conditions. Okay, and in terms of testing, oftentimes that when we looked at the testing, we kind of mentioned about states. To look at the state coverage, look at the state coverage. Coverage is kind of like you're doing the partition testing. Look at the state coverage, you need to cover all the states. Okay, and look at the transitions, you need to do the transition coverage. And particularly when you look at the input, you look at the input coverage related to the outgoing links. Okay, and looking at that from the perspective of the partition coverage. Okay, and with the output, we typically with the testing we are not really focusing on in the finite state machine testing. We typically use the output as a part of the result checking. Okay, so when we check the result, when you given this input in this state, what kind of transition did you make, and what kind of output are you producing? Okay, in a sense, you can think of the transition you select is a part of the quote-unquote output, okay? Because that's a part of the result of your giving this input on this condition, okay? And then you can look at that and the transition you take, and as well as the particular output that you produce to verify that whether you did it correctly or you didn't do it correctly, which is actually used as a part of our so-called oracle problem. Checking the result, are you following the right link and producing the right result and end up in the right state or not, okay? So those are the 4 basic elements with the finite state machines, okay? But what we have seen here is what we call the graphical representation of the finite state machine, okay? And we talked about those different states and the different transitions and the input and output. We can represent those things with some other forms as well, okay? So we can use these graphs, but we can also use lists and tables to represent those things, okay? So for example, that over here, what we can do is for those things, we can say, okay, in terms of the states, I can list all the states, A, B, C, D, E in this case, okay? Transitions, I can list all the transitions. I have AB transition, BC transition, CD transition, and CB transition, and DC transition, and DE transition, and EB transition. So I can list them all, okay? And then well, I can look at the input and output associated with those transitions, okay? So if I produce those kind of a list with all the states, all the transitions, input, output associated with those transitions, I can represent all the information in the graph as well, right? Okay, so that's another representation, okay? So we need to be kind of familiar with the different types of representations, okay? And you should feel comfortable working on those things. So for example, that with this graph we have over here, okay, we can list the states, okay? So states will be A, B, C, D, and E. So we have states, okay? So that we list the states, okay? We can look at the transitions, okay? Transitions, we have the A, B, and we have the B, C, and so on. So we can look at all the transitions, okay? And what is more, with the transitions, we can say, okay, not only I want to say the transition, okay, I also want to say what's the input and output associated with that transition. Okay, so I say, okay, AB, some IO, BC, some IO, each of those things, what's the input, what's the output associated with those, okay? So for example, with AB, as a AB, I don't really need any input because whenever I power up, after I power up, I always go to mobile station initialization, okay? So I don't need any input, I don't need any output. I can specify that like that. And then I have B, C, I don't need any input, I don't need any output. And from C to D, then I do need some input, okay? I have paging, okay? And then I don't have an output and so on. So I can create this kind of thing to represent my finite state machine, okay? And of course, then you say this one is somewhat kind of chaotic and not very structured, okay? So you can do the things with a more structured way by using a table, okay? When you use a table, essentially what you have here, you have a state A, B, C, D, E. So what I can do here is that I say A, B, C, D, and E here. I have A, B, C, D, E here. I can say, okay, here is from something and here is 2 something. So I will say, okay, can you go from A to A? Okay, I don't want you to go from A to A, but I want you to go from A to B. So I said, okay, A to B is okay, but not others. Okay, and I can do this, and then I can look at what's the input and what's the output related here. Okay, and so on. So I can create those kind of information as well with this table. Okay, so we can see that with the basic elements of the finite state machines, no matter whichever representation you use, remember you need to represent those 4 elements. Okay, the 4 elements is the what? First, state. Okay, you need a state, you need the transitions, and you need the input and output associated with those transitions. So as long as you can represent all those 4 elements specified for your finite state machines, you can use whichever form. And the commonly used forms are graphical form, this kind of list form, or this kind of tabular form, or matrix form that we use often to represent the finite state machines. Okay, so should feel comfortable with this kind of a transition between the different forms. Okay, and so let's take a break right now, and then afterwards we kind of look at some of the basic ideas about this, and then look at those different representations of what their advantages and the disadvantages of those different forms. Okay, so let's take a break for now.
79.
Some more questions. Any other questions?
These, I don't know, like, you know, you write to them. Some of them are little bit, like just one checkbox.
The number of questions will be the same.
There were like 9.
No, there are 12 or 10. Oh,
The
6.
second one was really like false and radio buttons.
Second one is from 10,
12.
9 and 10 and 11 and 12.
I did 9, 10. I got 80
Yeah.
on that, and then 11 and 12. It's my average so far.
I will press it. So home is on the so I start home.
Yeah, generally. but seems to be there some problem with the platform. For that, I need to take time out.
Did you start testing? No.
Okay, let's go back to our class. Okay, so we talked about the financing machines and how to represent the different elements of the financing machines in different forms. And actually, we talked about the three commonly used forms that to represent the finance state machines, the graphical form and the tabular form and the list form. Okay, and we can discuss a little bit about their advantages and disadvantages before we move on to other discussions about finance state machines. Okay, so if you look at their different representations, okay, the graphical form like this is typically fairly intuitive and really nice to look at and carries lots of information. Okay, so typically if you can use a graphical representation, typically people trying to use a graphical representation because it kind of conveys some of the information more directly and with less ambiguity. Okay, but the thing that if you want to look at this kind of things when it's getting more complicated and getting bigger, it's probably going to end up with a messy graph. Okay, and also there is also kind of a problem if you want to process it with computers, with machines. It's probably not directly kind of easy to process directly. Probably it's easier to represent them in some other data forms and structures. Okay, so that's the advantage and disadvantage of this. So for understanding purposes and for illustration, for all those kind of things, the graphical forms are great, and so the graphs are great. But for machine processing, is probably we will translate it into some other forms. Okay, and then you look at the two other forms we look at it here. Okay, with the list form and with the kind of matrix form. With the matrix form, is the advantage is that it's really kind of consistent and regular. Okay, so it's really you look at this and you can look at the rows and the columns that they are very meaningful to people reading those things, and as well as to look at for machine processing, it's kind of easy to process those kind of things. Okay, but if you want to store them in for large systems, then one of the observation is that when you look at the normally for finance state machine, when you have a large number of states, you don't usually have a fully connected graph. Each state is only connected to a few other states, not to all the other states. Okay, not to a large number of states. Okay, in that case, then you will end up with a lot of those empty entries. Okay, crosses or NAs. Okay, you can put in that are not available, they're not allowed, or crosses. Okay, so in that case, then you end up wasting a lot of storage space to store those kind of things. So in that case, this list kind of form is probably a more compact form of this processing. Okay, but for the list form is that when you for representation, but for processing, maybe there's a disadvantage. So you don't know which atom to look at until you really look into the list. Okay, so there's some disadvantage in terms of the access, although you get savings in storage. Okay, but the thing is that we should be equally comfortable with any of those, any one of those three representation for our finance state machines. Okay, so now let me go back to we looked at the finance state machines. Okay, and looked at their basic elements there. Okay, so we can look at their. We looked at why we do this and the basic idea and the finance state machine as a graph. Okay, so essentially we have the represented by graphs, and then we have the states and the nodes. Okay, which represents something which maybe in the example so far we basically represent some kind of status of the system, or they're in the process of doing something. Okay. and we can identify those states. Okay, and we may also associate some other properties with the states or nodes in the graph. Okay, so if we associate some other properties, we call those node weights. Okay, which may represent all kinds of additional information. Okay, and we also looked at the links and the link properties. So we use the links to represent the state transitions. Okay, and the labeling of the links is often by the nodes they link from A to B. Okay, so we say AB. So AB is different from BA. Okay, AB link is different. So it's directed. AB is not the same as the BA. Okay, and we may have some other properties associated with the links. Okay, and so for example that in the classical finite state machines, we associate the input and output with the links. Okay, and so when you look at those finite state machines, okay, it can take various different forms. Okay, and so there are several different ways of classifying finite state machines. You can classify them by the input, output, classify them by the state, what they represent, and even some other classification are possible. Okay, in the classical literature of about finite state machines, you often hear about the Mealy model or Moore model. Okay, which are not terribly important, but it's really kind of more for historical reasons. Okay, so I don't think I want to emphasize that as much as to mention that Mealy model and the Moore model are some of the things based on their way how input and output are represented. Okay, so in the Mealy model, both input and output are associated with transitions. So that's a normal case we deal with here. With the Moore model, that they represent the output represented as a separate state. Okay, so when you produce something as the output that goes to that state, and then go from that state, you go on to the next one. So you end up using a little bit more states, the number of states to represent the same kind of operations. Okay, so not terribly important, but in our book and in our discussions, we don't really distinguish between the Mealy and Moore model, because we typically, if we need, we can represent the output as a part of the transition as well. Okay, and there are also classification classified by what the states represent, and actually this one is something that we kind of make a little bit more distinction in our class, because later on, when we look at their control flow graph, okay, it is really more of their kind of the so-called type 2 model we will be looking at. Okay, type 1 is the classical finite state machine. A state basically represents a state or a status or snapshot of the system. Okay, so you can think of it's a state or status or snapshot of the system. Okay, and you can move from that one state or status or one snapshot of the system to another snapshot of the system. Okay, so in that case, if your states are just snapshots of the system, when you do something in the system, then it's through the transition. Okay, so in that case, all the actual tasks, activities, input, output are associated with their transitions. And the states are basically a snapshot of the system or status of the system, where you may be associated with certain values, a certain kind of conditions, characteristics, but not actions. Okay, so that's the classical type 1 finite state machine. There's also a type 2 finite state machine. Essentially, whatever you do is represented as some kind of state. And the transitions is basically give you a sequence of whatever you do. You do this one, you do that one, you do that one. Okay. So traditionally we have some kind of flow diagrams. Okay, so for example, that you have some of the scene here, like here. You have the tasks. Okay, so you say task 1, 2, 3, 4, do this, and after 4, repeat. After this, repeat 2. Okay, and so you basically say go back to 2. Okay, so in that case, is that you're doing this 1 here, doing 1 first, and then you're doing 2, you're doing 3, and then here is a 4. Maybe under some condition, you say you go back to 2 again. Okay, so in that case, each of them represents some task or some part of the task. Okay, and then what you have here is then essentially with the transitions, you just say the ordering of the task. You do this first, then do this, do this, do this, and after this you repeat 2. So you're going back to 2, and then do 3, do 4, and so in this case you may have an infinite loop. Okay, and actually sometimes we do have an infinite loop, and that's like for example, oftentimes people say, what is the operating system? Is basically infinite loop of fetching the user command and execute the user command. Okay, forever. Okay, so. In this case, is that each of the specific tasks is represented by a node or state. Okay, while the transitions are essentially give you the order information. Okay, so the order information or the precedence information. Okay, which comes before what? Which one comes before which? Okay, so this is our so-called type 2 finite state machine. Okay, that's the type 2 finite state machine. And later on, when we look at this, the control flow graph, okay, and some of those kind of things, that will be the type 2 will be dealing with. Okay, and sometimes that you may have mixed type of the type 1 and type 2. Okay, so what we have there is actually, if you look at our example here, some of the things that you see here, this power up is basically you say, okay, you can think of, is that a condition or is that action? You say, okay, if you consider that action, that's fine. That's the action power got turned up. Okay, and then after that, you go to here, mobile station initialization. When you do the initialization, you're doing a lot of things, right? And then when you look at here, mobile station idle, you're not doing anything there. Okay, so in a sense that you have some of the states representing some of tasks, some of the states representing a snapshot. Okay, and in this case, this transition is basically only a relationship between one thing followed after another. Okay, and then one thing followed by this one, and then over here you do have some input output. Okay, and then you do here. You have this system access. You are doing something here, and you have this mobile station control. So in this case, we do have a kind of a mixture of type 1 and type 2. So it's not terribly important to have a very clear distinction between type 1 and type 2, as long as there's no ambiguity about what you are representing and what is the meaning of that. Then you can mix the type 1 and type 2. But later on, when we deal with control flow testing, we are exclusively dealing with the type 2 kind of finite state machines. Okay. So those are a little bit about the type 1, type 2 finite state machines. Okay. So the type 1 is some of the classical mini model. Okay, and we have some other things. Like, for example, that when you look at some of the web testing examples, if you, I think I have some pictures of things here. yeah, some of the things like this, pictures about this, if you ignore all the numbers there, and you look at the things you have there, when you look at the, with the web testing, you can represent in different web pages as states, okay, and then you can represent those kind of loading of the web pages as the transitions, okay, so each of the web page is a hypertext linked to various other pages, so you click on that hypertext link, then the other page will be loaded or some action will be carried out, okay. So once it's loaded, it's there, and so in that case, each page is really a state, and all the actions takes place during the transitions. Because when you do the computation, when you're doing the display, when you do the loading, that's all there during the transition. Okay. So that's an example of this type 1 finance state machine. Okay, and so that's then the type 2 finance state machine is a kind of the things that the control flow graphs, the flow charts, and those kind of things that we looked at before. Okay, and we will deal with that a little bit more. Okay, and so we talked about this, and we talked about the finance state machine representation. You can represent it in various different ways, and you can have the list representation as well. Okay, and now we know what is a finance state machine. There's the 4 elements, or the types of finance state machine. And now our central purpose here is not just to understand the finance state machine. We want to use the finance state machine for testing. Okay, so this is what we are going to do. Look at the finance state machine and the problems represented in the finance state machine models, and then look at the testing issues related to that. Okay, so when we looked at it, what are the typical problems? If you want to represent a system using a finance state machine, what are the typical problems? Okay, so look at the 4 elements. We have states, we have transitions, we have input, and we have output. So if we have those 4 elements, the problems can be with one or more of those elements. Okay. So when we look at the states, we may have some of the states missing, some extra states, or some incorrect states. So those are the problems that we may have with the states. Okay, you say, okay, so how do I deal with that problem? Well, if you deal with that problem looking at the states, we talked about when you create your model, you need to create this list of states. And better yet, your list of states should form a partition. They should be mutually exclusive and collectively exhaustive. Okay, so you should not have any of the missing states. Okay, because they should be collectively exhaustive. It covers all the possible states your system may have. Okay, so the missing states and the extra states are kind of dealt with as part of this thing by the identification of the states. We can apply our same kind of principles when dealing with the partition testing, looking at whether you really form a partition or not by looking at the states. Do you have anything more, anything extra, anything missing? Okay, and also sometimes we also need to look at the incorrect states. For example, that do you have those states that really overlap with each other? Okay, or you have states that are incorrectly representing what is going on with the reality, with your software, with your implementation. Okay, and so that's a missing extra or incorrect states. Okay, so a lot of those things can be dealt with during the model construction stage, when you try to enumerate all the states, identify all the states, and classify them. Okay, and transitions, you may have again. You can say, okay, I can list all the transitions, and are there anything missing or anything extra? Okay, or anything incorrect. Okay, so in this case, we probably do a little bit less with the overall partitions. Okay, because when you look at the transitions, you are not looking at all the transitions all at once. Typically, you look at the transitions from one state at a time. Okay, because that's really naturally how we define the transitions. Transitions are from one state to another state. Okay, if a transition is from one state to another state for any given state, we want to see how many transitions I should have. Are there anything missing, anything extra, anything incorrect? Okay. So consequently, when we test for transitions, we typically test for the things with respect to the originating state. Okay. We don't usually test with the destination state. Okay, because of the thing that with the sequencing of the things, we always say, okay, from where to where, and so it's easier for us to look at from where to where, instead of from anywhere to this destination. Okay, so but when we look at that, that testing can be modeled again as a partition problem. For any given state, what are the possible input? How do we deal with those possible input? Okay. Do I have the positive input partitioned into the mutually exclusive and the collectively exhaustive subsets? If so, then each of the subsets will be associated with the one and only one link going to somewhere, a unique destination. Okay, so we can see here with the missing, extra, or incorrect transitions, we can using that property from a given state, looking at all the outgoing transitions, and perform that test. Okay, and we can look at the input problems. Input problems is really a kind of associated with the transitions, looking at from each state, what are the possible input and what are the possible transitions. We can deal with that problem. Okay, and then with the output problem, we typically use that to check whether we get the correct output, and typically we look at not only the where you end up with, but also what specific output you produced. Okay, and as I mentioned, in a sense that you can think of the abstract notion of the overall output for your system is the produced output plus the where you end up with. Okay, that's as the kind of a collection of the output. Okay, so the basic approach, as I mentioned here, is we deal with some of the missing extra states and some of the transitions as a part of the finite steam machine construction stage. Okay, we're looking at whether any states are missing or any transitions are missing. Okay, and then after that, we try to achieve so-called node coverage and link coverage. Okay, so essentially the thing is that we want to look at whether we can go from somewhere to visit this state or not. Okay, remember here one of the key difference between this state visit and the state at the list is that those states are not isolated states. States are linked through some transition from one state to another. Okay, and so we have to look at what happens from this state to another state to another state. So if you want to reach that state, you don't just go to that state. You need to start from somewhere to reach that state. That's the basic idea of a finite state machine. Okay, so if that's the case, then let's look at some of the situations. Okay, so we can look at this one here. Okay, so for example, here what I have here is that I have the 1, 2, 3, 4. Those are 4 states. Okay, so my collection of states is 1, 2, 3, and 4. And then I do have some of the initial states. So the system always starts from here. So I say start, okay, or the initial state. Okay. And in this case, do I have a final state? No, I have a kind of an infinite loop here. Okay. So what I have here is that if I want to visit 1, okay, state 1, I can just go to here, visit this one, right? Because it's an initial state, I can always start from there. I can go initialize the system. Okay, so if you think of this as the operating system, you boot the system, and then you start processing customer request. Okay, and you will maybe fetch the request, process the request, and go repeat. Okay, and so on and so forth. So say I can do this. Okay, I say, oh, okay, this is the case. I did this, so I can check this off my list. Okay, and then I say, okay, what can I do? I can do this. Okay, and let's look at the coverage here. Okay, so I did this. What can I do to get to 2? In order for me to get to 2, I need to start from 1, and then I need to get to 2, right? They're following this link. Okay, and so I say, okay, now I cover this one. Okay, so I start with 1. I did the 1 that cover this one. Okay, so you can think of this one as a here, this one as a cover this one here, and then I say I want to cover 3. Okay, how do I do it? I need to start from 1, going to 2, then going to 3. Okay, which covers this thing? I say, okay, I cover this thing, and then I can say 1 to 2 to 3 to 4. Okay, when I do this, I cover this thing. Okay, so I say, now I covered all of them. Okay, and so what you can see here is that with this kind of things, if you think of this, if you're trying to reach those states, okay, so those are your test cases. Okay, those test cases you go to 1, go to 1 and 2, and 1 and 2 and 3, or 1 and 2 and 3 and 4. Okay, you say you have test case 1, test case 2, test case 3, test case 4. So you have those 4 test cases to cover all the states. Okay, you may ask, say, oh, if I do this, I don't really need to do those other things before. Well, you still have to visit this state, visit this state, visit this state. So it's probably better to identify them as separate test cases so that you can clearly distinguish which states are you visiting. Okay, and so this is the state coverage. State coverage. Okay, what about my link coverage? Okay, look at the link or transition coverage. So I also try to cover all the links. Okay, when I did this, actually, when I did this, I had a 1 to 2, 2 to 3 covered, 3 to 4, and 4 to 2. So we have those links. Okay, when I did this, when I did 1, I didn't cover on any of the links. Okay, when I did 1 to 2, this one is covered, and then this one is covered, this one is covered. But with those 4 test cases, I haven't covered this 4 to 2, so I need to add this one so that I can cover this. Okay, but in general terms, you may have multiple outgoing links, and you have loops and things like that. So when you try to achieve the state coverage, typically you have not achieved the link coverage yet. Okay, so you want to, in addition to the state coverage, you want to do the link coverage. Okay, you say, okay, what's a systematic way of doing the link coverage? Well, a systematic way of doing the link coverage is that you go to each state and then try to look at all the links originating from that state. In that way, you can combine this link coverage with the state coverage. Okay, so for each state, you look at all the outgoing links. Okay, in that case, whenever you achieve the state coverage, if you added that for every state, you look at all the outgoing links, all the links should be covered as well. Okay, so link coverage can be combined, rolled into the basic state coverage. Okay, and doing those kind of things. Okay, so for example, that in the general terms, that let me just go back to use this example here. Okay, we had this example here, and actually let me use a little bit more complicated example that can illustrate some of the points a little bit better. Okay, let's try to use this example. This one is a little bit more complicated state transition diagram. You can see here that this is an initial state, and this is the final state. You transition out of this one, okay, to the some kind of higher level state. Okay, so you can think of this one as the initial state. This is the final state, and you go out. Okay, so with this one, you have a few more different transitions. For example, if you are doing the state coverage, you can do this one, then go down this one, go down this way, go down this way, go down this way. You need 1, 2, 3, 4, 5 test cases to cover all the states. But when you look at the number of links, you have this 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 links. Okay, and if you count those two, you have 11 links. If you don't count those two, you have 9 links. Okay, so those 5 cases that you essentially covered this link, this link, this link, and this link, but you haven't covered the other links. Okay, so what do is then you can try to look at this one and look at all the outgoing links. Can I cover all of them? Okay, and then when I get to this one, I try to cover all the outgoing links there. When I get to this one, I try to cover all the outgoing links. So it's this one and this one. When I get to this one, I try to look at all the outgoing links. So either go down or go up here. Okay, so I can combine my link coverage with my state coverage to get to this kind of finite state machine coverage. Okay. But then you said, okay, you had something about the state coverage. Seems to be fairly straightforward. But what if I have any arbitrary kind of finite state machine? How do I ensure I have the state coverage? And what's the kind of general rules I follow for my state coverage? Well, generally, this has become a kind of in the graph theory. It's a state transition or node traversal problem. Okay, you need to visit every node in your graph. Okay, and so typically you can apply all kinds of algorithms to it. Okay, and typically people use some kind of depth first or breadth first or some kind of algorithm to cover all the things. So for example, that you might be looking at going down this one, going down this one, going down this one, going down this one to cover, and you can go down this one and then look at whether there are anything else going out from here. Okay, you say, okay, going down E1 to E2, E1 to E4. Okay, so in that case is that you go cover E1 first, then cover E2, cover E4. You are doing the breadth first. Okay, doing what's my next state from where I start, not going into depth first. Okay, so you can apply any of those algorithms do your state coverage. But the key thing there is that no matter whichever algorithm you apply, you maintain a list of their states, and then you try to cover them all. Okay, so that's a basic idea about the state coverage. Okay, and then for each state you visit, you can look at all the outgoing links. In a sense, if you think of this, really with the testing, probably we would prefer breadth first than depth first, right? Because if you think of breadth first, is that you visit a state and looking at all the things that you can reach immediately from that state. Okay, so you not only visit that state, but you're also looking at the link coverage from that state. Okay, and then look at all the states that you can reach. Okay, and then take the next state and do the same thing, and take the next state to do the same thing. Okay, so I would argue for testing purpose, breadth first is probably more naturally fit into our finite state machine testing, because we are not only covering the states, but also we are looking at the transition coverage, to look at the link coverage, because link coverage is naturally associated with the states, and look at all the states, other states you can immediately visit from that state. Okay. Of course, you say, oh, what if I have a loop here? Then I can, or I have multiple paths to something. Say, for example, from E1, I can go to E4. I can go to E4 also through E1 to E2 to E3 to go to E4. But if I'm here at E3, I say, okay, what are all my outgoing links? This one going to E4. I have visited E4 already, so I don't need to visit E4 anymore. Okay, but at least I can identify this transition, see if I can make the correct transition or not. Okay, and then I can also look at from here. Can I go to something else? I can go to this E5. Okay, so I can look at this to come up with my testing. Okay, so that's the basic testing strategy for finite state machine testing. Okay, we look at the basic coverage, look at the node coverage, look at the link coverage, and the link coverage is basically done as a part of the node coverage when you visit each node, look at all the possibilities of outgoing links. Okay, so we basically try to check for the missing and the extra state and the links during the modeling construction, essentially looking at whether you have more states, less states, and whether they have the correct kind of identification. And you can first, with model construction, this is kind of the same as with any of the other model construction. We always first have to identify what are the information sources that we can collect the information about. Okay, and then you can construct your initial finite state machine, and then you refine and validate. Okay, and so when you identify your information sources is actually where you can say whether your finite state machine is a black box or white box. Okay, so your information sources can be the external functional behavior of your system. Okay, can be the specification, usage scenarios. Actually, for example, we mentioned about one type of specification is the so-called behavioral specification with finite state machines. Okay, and in fact, our example here is really a specification of the system, what your cellular communication system should be doing. Okay, so you can do this by looking at the external functional behavior of the system, and sometimes you can extract this thing from the usage scenarios. So in some of the development methodology, people say, okay, what are your use cases? Okay, come with your use cases and test cases first before you can implement your things. Okay, so people look at the use cases and look at the use cases in the object-oriented design and implementation. Okay, and people use that at some of the test cases, test scenarios, and design your system to pass test when you adopt the so-called agile development or test-driven development. Okay, so you design your test cases first, and then you design your system to pass those test cases. Okay, and so in those kind of situations, oftentimes you use those things to specify your external behavior. So your finance state machine, in that case, will be the black box testing model. Okay, and you can use also addition to that black box view, you can also capture the usage information. How often you are using this one versus how often you are using that one into the so-called usage model. And in that usage model is later on we will be dealing with as the so-called Markov operational profile. Okay, so we will deal with that later on. Okay, you can also extract those things from your internal execution and internal design. Okay, so for example, that we often have those kind of flow graph about oh, I'm doing this and then I'm doing this and then I'm doing this and then I'm doing this. Okay, or if I have the code. Okay, if I have the code, then I may end up having something like this. Okay, yeah, this desk. Okay, if I have the code, I may have something like this. I say I equal to 0 while I less than equal to n. I do something here and then do some task here. Okay, and then I increment I, for example, and then I get out and then do some of the things. Okay, so if I have this, I can come up with the flow, a flow chart of this thing. So I basically say, okay, I equal to 0, this one, and then I come into a while loop. Okay, and a while loop, and then I have this condition, I less than equal to n. If it's true, I do this one, this body here, task A, I do A here, okay, I do A here, and then I do I++, and then I go back to here, and if it's false, I come out, okay? So what I end up with here, this is my finite state machine. And actually, it's the one special type of finite state machine is called the control flow graph. Okay. So I can kind of start with this and convert this into my finite state machine or into my control flow graph. In this case, what I got here is I have white box testing model. So basically, my control flow graph or my finite state machine will be used as my white box testing model. Okay, so I can do this. Okay, so you can see here is that sometimes when we talk about, oh, what kind of testing techniques are you doing? You say, I'm doing black box testing, I'm doing white box testing. That's not really talking about the testing technique. That's talking about different types of testing. Okay, when you look at the different testing techniques, is that I'm doing black box finite state machine testing. I'm doing white box finite state machine testing. Okay, I'm doing the usage-based testing with the finite state machine. In that case, I need to add some probability, so that I'm using the so-called Markov operational profile for my testing. Okay, and so as we can see, it's a finite state machine testing as a testing technique can be black box, can be white box. Depends on where you get your information to construct your model for your testing. Okay, if you construct your model based on the external behavior and functionality of your system, you are doing black box. If you construct your model based on internal implementation or design, internal design or implementation, then you are doing the white box testing. Okay. And sometimes you can build those things based on existing test cases, the program, the documentation, and some other things. Okay. The key thing here with finance stream machine is that you are not looking at the isolated pieces. You are looking at linking everything together. Okay. So essentially, when you identify those things, those states, they will be linked together through some kind of transitions. If there's something not linked together, there may be some problem you can detect. Okay. So let's take our second break. When we come back, we will wrap up this thing and probably also introduce the ideas about their Markov operational profile a little bit. Okay. So we'll take a break.
I'm trying to think if I've ever seen anybody use it. Oh, it's in that like corner by the door. I don't think I've ever seen it.
Almost every. And you have B blocks, B.
You free on all of Friday?
I don't know why in the A they don't have the plus. Like you start with A, then A minus, then the B you have the plus. B plus, B, B minus.
No, I thought I have here. I have things that I think a plan on.
I mean, practically speaking, you can schedule your classes now.
open now.
You can schedule your classes. Yeah, so you can decide, how you're gonna arrange your classes.
I know
can't
what
arrange-
classes.
You already know.
Yeah. Until the graduation.
So,
I
so
talk
You can't, you can't even enroll, you can't fully enroll yet, you can just add to the shopping cart.
Okay.
You have to speak with an advisor and then they'll let you.
I need to talk to my advisor. About who's
So I can just log in and add the courses to my.
You can, no, you can like save them, like, it's like a wish list. I wanna take these
But you're
courses.
not officially invited.
Who's your
advisor?
Ivan.
Graduate computer science at Tian.
I'm computer science, but not Tian.
Are you a graduate student too?
I'm a graduate.
I'm
Yeah.
sorry.
Computer science.
Everyone I bet you is Tian.
I just always thought this one's yeah. I guess I can learn this one. Since they're stressing me out about
You get the classes you wanted?
Or this one?
Yeah.
No, not even a single one. I was planning to get the database. No, I was planning to take it.
Make sure you just look down.
Database.
Get your opinion.
I comment about.
This is my note. Yeah, I think notes of leadership or relationship. It helped from those multiple choice questions. There's like definitions, fill in the blank, to help with something.
The seminar is
I
called.
don't
So I
take,
think this is
Got him, you got a
to make sure we're all like supportive or something.
I remember some stuff a little bit better, but to get 100% every time, it like minus every single sentence. All I know is like, this is like an example, like a person that has something, skip what we're going to read that. But if anything else, like about general ideas about leadership, write down every single sentence, you're gonna get it.
Yeah, that's what I'm saying, you need to make sure how much time it's in that thing. Security.
I don't think it's gonna be good. Is it included in?
Engineering, computer engineering.
I think it's credit,
How
but
about
it's
you?
not calculated.
Security engineering, that's like, I forgot, there was one person.
No, it's not.
Your undergrad
I'm just
also?
gonna take
Your
it.
undergrad or grad, right?
No, it's just
It's just in
undergrad
your
course.
college.
That's
I
regular.
don't know who I
Okay. So you go to your, my SMU is gonna stay on the side program advisor.
I'm undergrad
Oh,
course.
yeah.
No, it's not elective, not everything. It's not gonna be.
And you can email
I'm gonna have to do it, I'm like, I just, I'll try to.
Because I know
I'll
nobody.
be whoever, when she registered me,
That's undergrad.
the lady, she didn't reject, she didn't reject it. Last year, I remember when I registered class, I'm like, that's not.
Oh, so it's not elective,
Told me
not.
that. Okay. I don't know anything. I haven't looked at.
So I
You know,
think,
this year,
I'm not sure. So I'm gonna take the one, I'm gonna take I'm gonna take,
But aren't you computer engineer?
no, I don't have advanced.
See, you're undergrad.
I have advanced, but not advanced.
You're, you can still take the same classes, y'all still can be
I'm
friends.
gonna take which?
Undergrad.
No, we're in 2 classes.
See, he's a grad, y'all can share, y'all can be friends. He can be your friend too. Where you at?
Computer science.
He can be your friend.
And I'm gonna take class with Maya. We're already friends, I guess. We're all friends.
No, we have traded information. Keyword.
I'm gonna take class with Maya. Maya.
you know the person, right?
Young, like young, like young.
They have like
Young,
Maidmaster, Archmaester, like Gate,
Oh, yes, yes.
1 month,
Yes.
they just instead of having, one class every week, kind of like summer school.
Okay, let's go back to our class. Sure, this one is on. Okay, go back to our class. We talked about this financing machine as a testing model and then how to use that thing. And let's try to wrap it up now. Okay. And so we talked about identify the information source and how to construct the thing. Okay. So generally, with the model construction, with the financing machine, we first have to identify and enumerate the states. Okay, so the thing, as I mentioned before, that basically with the state identification and enumeration, that is, as what we said before, that the kind of partition problem, to try to find all the states. They are mutually exclusive and they are different from each other, and that they are collectively exhaustive. They cover all the possible states for our system. Okay, and one of the problems with this is that when you see any of the large systems, that then you have the so-called state explosion problem. Lots of states. Okay, when you have a lot of states, it's going to be very hard to test. Okay, so sometimes you will need to kind of do something to reduce the number of states. Okay, it's kind of like our partition things. Okay, if you want to have something partitioned too fine, and then you have too many items. Okay, so you want to group them into equivalent classes. So similarly, you want to have a state representing a whole category of things, and then you look at the linkage among those different things. Okay, and so for that, you need to sometimes to deal with that thing is that one of the common strategies is using the so-called nested or hierarchical finite state machines. Okay, so you maybe use some states as a collection of number of things. Okay, and actually this is the example I have shown you over here. Okay, so this is what we have here for the web testing. Okay, when you look at the web testing, if you represent each web page as an individual state, as an individual state, then you will end up with too many states. Okay, so think of the World Wide Web. There are billions of pages out there. Okay, so if you want to test them, you don't want to test represent that as the interconnect every individual page. So that's why people give you the kind of a site map and some other things, the sub-site map and those kind of things. So you can collect all the pages related to a single site as one page, and then look at how closely connected with this site, with another site, and so on and so forth. So in that case, what you end up doing is that you have this hierarchical modeling. On the kind of higher level model, you have each site as an individual state, and then you look at the connectivity among the different sites, and then you can test within the site, and then you look at the individual pages, or maybe you have more layers. Okay, site to subset, collections of sites. Okay, then individual site, and then subsets. Okay, and then individual pages, or so on and so forth. You can do this in various different ways. So in this case, we were using their engineering school website at SMU. So we collected the information about the connectivity among the different things. So when you look at that, you look at the connectivity. Sometimes you are not just looking at the structural information. You are looking at the connectivity to use as a guide to decide your hierarchical model. Okay, so you look at who is closely connected to who else. So you look at the natural clusters. Okay, so for example, with the SMU Engineering School website, we found some natural clusters. For example, CSE is a natural cluster, computer science and engineering. Okay, electrical engineering, E is a natural cluster. But then we also have some other clusters. Okay, for example, we have a graduate admission, graduate, all the things that relate to graduate education as a cluster. That cuts across all the departments because all our departments have graduate programs. Then undergraduate related things form some kind of cluster. Computer support forms some cluster. So your clusters are not necessarily aligned with your organizational structure. Okay? Sometimes it can be aligned with some of the actual usage, actual functions. Okay? And so you can form your natural clusters and then have your hierarchical model. So for example, over here, we have the index page to the engineering school website. Because it's accessed so often, we have itself stand as one individual state in our model. Okay? And then from index page, you can go to graduate admissions, go to graduate information, go to information data, undergraduate information, and then go to some other things. And so you can have those different kind of clusters of the things. So with the graduate admissions, then they actually have many pages within the graduate admissions. So we kind of group them together there. Okay. And with the graduate information, and there you have other things, and so you can group things together. Okay, and sometimes you can do this, and sometimes you can. In this case, we actually looked at some of the top pages that got access, and represent them as the individual pages, and then the ones that got access much less often, group them together. Okay, and so there are many different ways of grouping those things, but generally, with the finite state machine testing, for any realistic problem, any realistic system that people use, if you are not discriminating, you will end up with too many states. Okay, so you need to do something about it. Okay, so select the top usage ones, the important ones, as the individual states, and then lump the other things together. Or you can use some kind of functional, structural, organizational rationale to lump things together. Okay. In this our previous example, there is also things about this one here. So we have our cellular communication system here, making mobile station control on traffic channel, which actually includes lots of sub-functions. It's complicated. So we can have this as one state in the top level model. And then in the lower level model, we can expand it out. This one state, we can expand it out into some of the sub-states. Okay? So this hierarchical idea is a very interesting and a very useful idea that we should consider when we deal with their model construction for finite state machine. Okay, and then after that, then you look at the transition and the link identification, which is typically associated with the input for individual states. Okay, so you do the input analysis and looking at for what kind of input, what kind of actions will be taking place. That will help you with transition or link identification. Okay, and you identify the I/O relations. Okay, what's the input? So when you did the transition link identification, you typically use the input information. Output relations that you look at really that will be looking at the task oracle, where to check your problem with really correctly handled or incorrectly handled. Okay, so the key step here, the most important step here is really the link identification after you identify the states you identify the links, and that's really link the things together. Because if you don't link the things together, you end up with doing the partition testing, basic partition testing. When you link them together, that make it a finite state machine. Okay, if you don't. So we mentioned about the link identification and the problem detection. You can identify all the possible input for each state. Okay, and input values may be partitioned, so we can use our knowledge about the input partition. Okay, and each partition subset will be associated with some kind of state transitions. Okay, and so you can identify some of the problems. If you are on the undefined transition for some input, you have a missing state or extra link can be identified. Okay, so you don't know where to go, or you have extra link that link maybe should be grouped into something else. So missing state is that you say, oh, okay, I have something that you don't know where to go. So you find out the missing state, and sometimes you may have extra link. Okay, because your link is there, and actually links should be grouped with something else. So you say, okay, and what should I do with this? I don't know what to do, and actually this is a subpart of something else. Okay, and so you need to group that link into something else. Okay, and when you look at the actual states or missing links, which will be a little bit harder to identify. Okay, because you say, okay, I did this, I have some extra states there. Nobody is linking to it. Well, that may be there's a problem. You should have something all connected together. You have something not linked together, there may be some problem. There maybe it's the extra state, okay? Or maybe that state should be linked through something and you didn't link them. Okay? But that thing is kind of a little bit harder to tackle, because when you look at the individual state, if you don't have a link to that, maybe that's correct. You don't have naturally you don't have a link to that. You don't have a transition from your state to that state. Okay, but collectively, you have to look at from all the states, can I go to that state? Okay, so that one have to kind of, you have to look at the connectivity algorithm and collectively try to identify those extra states or missing links to those states. Okay. And so once you have your model, a basic model, you try to refine it and try to validate the model before you can use the model for testing purposes. Okay, so the state explosion is a major concern with the finite state machine testing. Okay, and we mentioned about we can use some kind of hierarchical modeling ideas, and we can use some of the importance and use some other information to identify some of the states and isolate some of the states and then group some other states together. Okay. Generally, if we want to do the finite state machine testing, we at most should have dozens of states, not thousands or millions of states. Okay, so a few dozens of states, that's okay. A few hundred is getting a little bit harder, but if you have thousands or more than thousands of states, then those a lot of graph algorithms, you will run into some of the difficulties with the kind of time-space requirement for graph algorithms. Okay, it will be hard to traverse through the graphs and things like that. Okay, so for those of you who are interested in that, and we do have an expert in graph theory and the applications, Dr. Matula, and he's still working on a lot of those graph-related things and mapping those to various different computer science-related problems. Okay, and so generally proper granularity is needed, and we can typically use some kind of a nested hierarchical finite state machines, and sometimes we can also use some of those usage-based testing ideas, looking at the highly used part represented as the individual nodes, and the not so highly used part group them together, and so on. Okay. So when you look at this finance state machine testing, it's typically quite suitable for the manual-driven software. Okay, when you look at the manual-driven software, you can kind of naturally each manual can be associated with a state, and then from one menu to another menu to those are kind of transitions that can be naturally represented as the transitions in the finance state machine. Okay, and with the manual-driven software, as long as you don't have too many menus, you generally can represent each menu as a separate state, and then the linkage among the menus will be the transitions or links in your finance state machine. Okay. Sometimes when you have a system that processes something, but not processing everything in one shot, with clearly identified stages and procedures following certain stages to accomplish something, you can use finance state machine as well. Okay, so that's another thing. And a lot of times that when you have interactive systems, okay, you can use finance state machines. Okay, because when you look at the interactive systems, it's actually you're looking at the customer's users will be interacting with the system and will be at a specific point that will be asked for some input, and you provide the input and the system will respond and so on and so forth. So you can use that finance state machine to model that kind of interaction among the different the types of their interactions and their intermediate state. Okay, and you can use this for control systems, object-oriented systems, and various other things. Okay, so you allow for any arbitrary state transition. Okay, and this arbitrary state transition will give you the power to kind of looking at the connectivity and looking at how things are done together by following through different states and transitions. But the key limitation here is the state explosion. Okay, how to deal with that problem? Generally, there are two general type of solutions. One is we mentioned about using the finance state machines, nest them. Okay, so you have a lower level models, finance state machines. Okay, and also you can nest finance state machines with other things. Okay, so for example, that within a finance state machine, you can say I just have a collection of individual pages. I don't really care about their individual states. I don't care that much about their interconnection. Okay, so in that case, you can say, okay, under this node, I have a partition model. Okay, so when you do the nested finance state machines and nested models, you're not necessarily always nesting the same model layer after layer. You may be nesting some model, some other model inside a different model. Okay, and you could maybe, for example, you can do things like also higher level. I have a partition, and then going down the higher level, I can have the finance state machines. Okay, so for example, when we did the testing, the web testing for the SMU website, SMU engineering school website, you can say, okay, I want to do on the higher level, I want to do the individual organizations, CSE, EE, ME, and computer operations, graduate of education, undergraduate education, finance, and something like that. Okay, and then I can look at so in that level, what I have there is a partition, right? Partition of all the web activities into activities associated with those different units within the engineering school. And then I can say I go into more details, test all the CSE related things. Okay. Then I can go to details of testing all the ME related things and so on and so forth. Okay. But then when you do that, there might be some compromises, okay? Because when you did that, you are really missing the connection. Say, for example, in this case, I did a graduate education as a separate item on the top level, and the CSE as a separate item on the top level. But when I do the CSE, naturally, it has something to do with the graduate education, okay, with the undergraduate education. So I cannot really cross this thing anymore, okay. So whenever you do the hierarchical modeling, typically you will be losing some of the basic relationship, but sometimes we have to sacrifice that to make our testing techniques practical and usable. Okay. So those are some of the ways of nesting the things, and then we can also use Markov chains and use usage-based testing ideas, okay, to rank them by the usage, and then so we can focus on the high usage part and maybe group the low usage part, okay. And so we can, when we do the testing, we talked about the basic state coverage. We can cover them directly. I had examples there. Link coverage start from state in combination with the input domain testing idea, so you can do the link coverage. So we talked about this, okay. And then there are some of the other issues we need to cover, like the implementation issues with sensitization, with the oracle issues, with various other things, okay. With sensitization issues, it's actually, if you have the model already, the sensitization will become easy, okay? Because your sensitization, what is the sensitization? You need to identify the input for you to realize certain things. Because in finite state machine model, you already identify the input to make that transition. So once you decided that this is the state I want to visit, then you just follow from the initial state, follow a few links until you get to that state you want to visit, okay? And those links will be associated with the input, because when you specify a finite state machine, you specify your input. So the sensitization in this case is easy because you did the hard job ahead of time, okay? In general, the sensitization is not always easy, but you will have to pay in some stage. And in this case, when you did the finite state machine modeling, you already did the input analysis, right? You already did the input analysis to identify under this input, I'm going to follow this transition to this state. So you already did that. So there, after your model is constructed, the sensitization will be fairly trivial. Okay. And the state coverage, you have a series of links with input. Okay. So as an implementation issue, we have seen something like this. Okay. For example, we have here, in order to visit 2, I have to go from 1 to 2. In order to visit 3, I have to go from 1 to 2 to 3. Just imagine you have a very long chain, lots of states, and you have just one initial state. Then in order to visit one state, and you have to go through a long chain to get to its previous state and then get to it, okay? So if you do this as separate test cases, then you'll end up repeating lots of things, right? So when you do this, you're repeating this whole thing here before you reach here. When you do this, you repeat this whole thing here before you reach here, okay? So it would be nice, it would be cost effective if we have some facility to kind of save some state. So instead of I always start from the initial state, I can start from some saved state and to reach additional states, okay? So that's kind of one of the things that with this finite state machine testing, we want to do. Or alternatively, you can handle a long chain and then allow you to stop along the way to verify each state, okay? So when you look at this one, this one is a kind of an important area for some of the test support, test automation. Okay, you can either have some facility to save the state or some facility to allow you to stop along the way and check other states along the way to your destination state. Okay, so that's an important implementation issue. Okay, and in some sense that a lot of software tools are helping us doing this. So if you think of the debuggers allow you to execute instructions, execute a program one instruction at a time. So allow you to stop at those different places and alter the values and examine the contents and the things. So in a sense, what you are doing there is that you're looking at the different states in your program execution. Okay, and check whether that state is correct, and then you can move on to the next state and then move on to the next state. So in that sense, you can think of that program debuggers as some kind of automated tool help for finite state machine testing. Okay, of course, your finite state machine testing may not be at that low level, instruction level. It may be at a much higher level, at a module level, at a function level, at so internal module level or external function level, or whatever kind of things. And the oracle is really you're looking at the output with the links, whether you produce the output. But also important thing to remember that the oracle, you look at the behavior. So the exact behavior is not only captured by the specific output that's produced from your system, but also your state transition you take. Okay, so your state transition and your destination state is also part of your oracle problem. You need to not only check, under this input, I produce this output, but after I produce this output, I'm going nowhere. That's no good. Okay, so after producing this output, I'm going to a state that is my specified, my expected state, where I can do additional things. It's not to a state that I crash, I stop, or I doing something unexpected. Okay. So those are some of the implementation issues. Okay. In your book, there is this case study. Okay. Oh, I'm sorry. I should have switched a little bit earlier. So I was talking about this sensitization issues with the state coverage and the capability to do these things oracles. So I covered those things. Okay. The case study is about the finite state machine for web testing. Okay. So essentially, what we looked at there is that you can think of web as a connection of different menus. Okay, so if you think of the individual web pages with the embedded hypertext links, those hypertext links is basically allow you to translate from one menu to another menu to another menu to another menu to another menu. Okay, and then in addition to that, we also have the facilities to have some of the things. For example, like we can bookmark things. We can bookmark after viewing this page. I can check my bookmark viewing a completely unrelated page. Okay, and so on. So when you look at this, their web applications had some of the similarities, but differences, also significant differences with manual-driven software. We said the manual-driven software is probably a good candidate for finite state machine testing. But with the web testing, you say, okay, I can do that thing, but then the thing is that when you have the look at the web and compare to the manual-driven software, there are some fundamental differences. There are some quantitative differences. There are also some qualitative differences. Okay, in terms of quantitative differences, is that in terms of the number of pages or number of menus. So in this case, if you consider each page a menu, is simply too many. Okay, typically a few orders of magnitude larger than manual-driven software. When you think of manual-driven software, think of for example, one of the typical manual-driven software people think of is look at the ATM machines, bank machines. Okay, ATM machines, you have only a few states, okay, a few menus. You're supposed to first probably you're supposed to use your card to access the system. So you have the login page. After a login page, then you have some menu selection, typically limited number of items. Okay, you can do some kind of manage your account. Okay, some of the account, and then you can do deposit, withdrawal, doing a few other things. Okay, and then you can they're doing deposit. They ask you the amount. Okay, and then decide whether that amount is within the predetermined limit or not. Okay, and so on and so forth. So you have a limited number of menus. But if you look at the web, even look at the moderately sized website, you have thousands of pages. Look at just engineering school website. Okay, we have thousands and thousands of pages. Yes.
So like a website, right? So what if you only like a few pages? Don't you have like a lot of backlinks and stuff? So I mean, is there different?
Yeah. It depends. It's also changing. Okay. So for example, a lot of e-commerce things. We talked about this ATM banking system, and you can look at a lot of e-commerce things. You have a limited number of sites, but then number of menus, but then behind it there are a lot of processing business logic and things. So you use that just as a front feed, and so that is different from a lot of those informational websites. Okay. So typically, for the informational websites, you have a lot of pages. Okay, but for e-commerce, typically you don't have that because you have a lot of computational facility building under the surface. Okay. So that's also a part of things that you have a traditional menu-driven software. You have a computational focus, but for a lot of web applications, you have the information and the document focus. Okay, so it started as more of the document only and the things, but now we have more of the kind of interactive processing. Okay, and in the web, your navigation and the page are typically kind of embedded together. Okay, so they are mixed together. And navigation and the information and the navigation typically mixed together. Okay, within the information you have navigation, and so you also have a kind of flexibility with the entry-exit control. So for example, with the typical manual-driven software, you have fixed entry, fixed exit point. Okay, with the web-based system, your entry point can be any page because you can type in the URL of any page and you can get to there. Okay, so you can enter into a website from any page. Although we oftentimes enter from the index page, okay, but potentially you can enter from any page. Okay, so that problem is actually not as bad as the exit page. Exit page is a particularly bad problem for the web because people stop browsing anytime. Okay, so unless it's some critical information with money, with business, with something, people probably won't log off from your website. Okay, they just stop browsing and that's it. Okay, sometimes they close the browser and oftentimes they don't even close the browser. Okay, so where's the end page of your browsing? We don't know. Any page can be the end page. Okay, and typically you don't have the symmetric things with the index page. The index page where most of people come to your site through the index page, but they exit, they don't go through your dedicated exit page. Okay, because they just stop and that's it. Okay, so when you deal with these things, and a lot of times when you process the information, you have to deal with those things and looking at that presents a lot of problems that we need to deal with, and also there are many layers. Okay, you have on the top you have the client, the web browser. Okay, and then you can look at it from the client side and from the server side. Okay, and from the client side you have your own operating system, you have a middleware, and you have your browser. Okay, and then from the server side you have the web server, you have middleware, you have database, you have operating system, and then nowadays you also think of not only this, you have the server. They may not have everything in the server. They may have a lot of things out there somewhere in the cloud. Okay, so you have even more complications. So that because from the user's perspective, you are using a browser, using a machine to access something, and access something that is a service provider, and that service provider may have a database in the Amazon cloud, and they have some other things in the IBM cloud and in something, and so they may have things all over the place. Okay, so that presents a lot of problems with when you look at the testing. Okay, so web testing, service testing, cloud testing, and all those things have a lot of problems. And actually, our group here at SMU is one of the pioneer groups of doing some of those things. Okay, we are the first group to publish a paper on their web testing related issue in the IEEE Transactions on Software Engineering. Okay, and we are now working on some of the service testing and on some of the cloud testing as well. Okay, so those are some of the interesting and challenging problems. Okay, but when you look at this, the problem is that you have a lot of problems that you need to identify and that you need to test. Okay, you look at the reliability. When you look at the web-based applications, generally people study this and say, what are the typical quality problems? Okay, one of the kind of important paper was a paper by Jeff Offit, and I think by him and maybe with someone else. He identified that for the web-based applications, the three most important quality attributes are reliability, usability, and security. Okay, so those are the three most important quality attributes for web-based applications. Okay, and for reliability, that is kind of similar to any of the other software systems. You want it to be reliable. Okay, you want it to be working and give you the correct result. Okay, so that is a kind of a common expectation for all the other systems. But for web-based systems, usability is also a major concern. Usability, how easy to use the system. Because for web-based applications, you put on the web, this is the so-called universal access mechanism. So it's universally accessible by anyone with an internet connection. Okay, and so in a sense, your user population is no longer limited to the specialist. Your user population is really everyone who has access to the internet, and so in that case, you cannot make a lot of assumptions about the user behavior, user background knowledge, users' sophistication with the programming languages, with the computers, and with whatever kind of things. Okay, so usability has become a critical concern that you need to strive for so-called universal usability. Security is a major concern because they're kind of open environment sharing, and you don't want to disclose and share those things that is not supposed to be shared. It's supposed to be disclosed. Okay, so those are some of the major concerns. And then when we did the web testing, we actually focused on the reliability aspect. Okay, So look at the failures, faults, and errors associated with the web applications. And then we can say, okay, what are the failures for web-based applications? Can be host or network failures, it can be browser failures, can be source or content failures, can be user problems, improper usage, and so on. Okay, so among those things, host or network failures, server failures, and those things are supposed to be taken care of by people who are working on the hardware, on the networks, on the servers, on those things. Okay, so it's not really more of the web-specific problem. Browser failures, then your individual browser vendors should be taking care of that. Microsoft should take care of Internet Explorer, and so Apple should take care of Safari, and then Mozilla should take care of Firefox, and so on and so forth. Okay, so that's a kind of, you can think of those one almost like a traditional software failures and the software product. Okay, but then when you look at the web, you provide some content. Okay, you have something. I put up a web page for our class 7314, 15314 class. So I have some of the things. I have links to homeworks, homework assignments, to syllabus, to some slides, to some other things, and those things, if I make a mistake, then the student, you will not be able to see some of the things or go to the wrong direction or something like that. Okay, so I should really be responsible for those kind of things. The contents I'm responsible for. Okay, so we really need to focus on the source or contents failures from the information source provider point of view. Okay, and then deal with the problem. We can also look at some of the use problems and the navigation problems. Okay, and so we focus on the reliability problems before, and actually recently a couple of my students also start to work and focus on the usability problems as well. Okay, looking at how easy to navigate in the web and how the web layout can be evaluated for usability and the purposes to improve the usability. Okay, so what we did here is that we kind of looking at the web source and the contents components, look at what is involved there, and looking at their connections. We come up with basically some kind of hierarchical model. Okay, but the big problem is that we have too many pages. Okay, if you have too many pages, you have to do something to group them together. So we tried different ways of grouping. We look at the grouping based on the organizational unit, grouping based on the usage, grouping based on the external functional linkage, and so on. Okay, and so we did lots of those things. But the basic thing is that you can represent each page as a state in your financing machine, but it will not be practical for any realistic website. Okay, so you have to do something to reduce the size of your model. Okay, so later on we'll be looking at some of the kind of usage-based testing ideas to isolate some things out, and we just have the high usage ones represented as individual pages, as individual states, but the low usage ones are collected together. Okay, and so that will be one way of overcoming this kind of problem. Okay, and so let me stop here and see if you have any questions. Yes.
Do you have any homework this week?
Not this week. I will probably assign something next week. Any other questions? Next week, I think I will be discussing the midterm exam things. I'm still trying to figure out. I had a student request an extension and had some extraordinary circumstances, so I cannot really discuss the exam questions and answers today, but I'll try to have that resolved by next week, and so I can discuss midterm exam questions and answers, learn from our mistakes next week. Okay. Okay, so we'll end today's class a little bit early.